Hello, I'm Dr. Mohamed Nezami. Greeting to you. Welcome back to my YouTube video channel. I welcome you back. As you know, I have been doing a lot of various kinds of RF and microwave design videos. They span from anything from SATCOM terminals to waveguides to microstrip lines to active microwave and RF circuits. So I welcome you to please sign up to my channel if you don't mind and subscribe. I would appreciate if you do that. Okay, so today I'm going to be talking about a concept which is very important in designing waveguide structures, mainly for SATCOM um, devices and for also ground equipments as well, such as radars and even medical equipments. Um, as you know, I have covered um, several videos on the design of impedance matching using multi-section transformers. As you can see, here's one in here where and then there are other ones as well. You can go back to my video channel and watch those. But I did not cover um, the concept of microwave implementing those multi-section impedance matching devices implemented in waveguides. And that's what I'm going to do today. Okay. So what I'm going to do today, and please, okay, the slides of the lecture are, if okay, I did the slides here. Basically, I put them on LinkedIn, and you can check out my account in here, so you can find them there, PDF files. And then if you're seeing the slides, well, I guess just this is for if somebody's seeing the slides, they can scan the QR code and get to my video channel on YouTube. My contact is usually this email here. If you'd like to get in contact with me, I work as a freelance designer. You can buy my services. I charge by the hours, very cheap rate, $20 an hour. The first several hours is always free for consultation. I best work remotely with you. If you have a need for an RF and microwave designer, I work with you from the concept to basically fab files and BCBA files. I work with you. I would help you, guide you through the manufacturing process of the BCBs and assembly of components on them, and then work with your engineers, also support them in the final testing and verification. Also, another area that I work in, which I have many clients that are very satisfied, is if you have a board that has obsolete parts on it, I take that board, if you have an existing artwork for it, I take that and then I can upgrade that so you can actually rev it into a new board, which mechanically and package wise, you don't change anything and it would still be the same board, except I would get rid of the obsolete parts and replace them with more modern parts. So, modernization of existing designs. Okay, and then also I have a workshop training that I hold every year, few times a year. This time we're going to hold the design training one and two. Okay, and this is going to be 2 weeks. Okay, and this is the usually I hold this in Jerash, Jordan. I forgot to tell you this. I operate of Jerash, Jordan, and that's what you see in the background there is and this is here is my native town. I hold this locally in the town. There are several hotels like the one I show here, and the fee is very reasonable. So it's $2,000 per course. Okay. And then I handle everything except you handle the travel, basically the ticket. Okay, so let's get to waveguide transfer impedance transforming or impedance matching transformers. Okay, as you know, the current implementation is for rectangular waveguides. Okay, and I will talk also about a square waveguide case toward the end of this session. So a waveguide, as you know, it has two dimensions, basically the height, we call it B, and the width, we call it A. Some people call this the broad wall side, and this is the width. Okay, very simple, very straightforward. I don't. I'm not going to start from zero with you on this. I always assume that I'm doing a little bit more advanced say lectures, so I'm assuming you already know this and have used Maxwell's equations to solve all the properties of this, such as the cutoff frequency, the attenuation loss, and various propagation modes into it, and so forth. Okay, so what is a transformer? Like I said, I did cover the microstrip multi-section quarter wavelength transfer impedance matching transformers in my lecture, and you can find them there. And basically, we use either closed forms or we use MATLAB built-in functions, or we use most commonly, like I'm going to use here in a bit, is the tables in Posar book. And basically, what we do is you get the input impedance, the output impedance, and then somehow, based on the bandwidth, you would come out with the order of the transformer, and then of course, the maximum return loss. And so with those two things and the frequency, well, not the frequency, but those two, just the maximum return loss and the uh, the bandwidth, and then you can figure out the order and go into the tables, and then it would spill to you the various sections and impedances from the source to the load. Okay. All right. So just to cover the basics, okay, let's get back to the basics. So when we're using a quarter wave transformer in transmission lines, and this is also valid for a waveguide, you have an input impedance, or yeah, I'm sorry, you have a source impedance on this side, which in this case we call the Z0 because we're assuming it's a characteristic impedance of 50 ohm, for instance. And we have a load, and we need to match them so that we get minimum reflections, okay, and maximum transfer of power from the input to the out. And we derived basically the quarter wave input impedance equation, which is here. So basically, the input impedance on this side is really the tangent of beta L. Beta is the electrical length, okay, which is 2 pi over lambda, okay? And L is the physical length, okay, which is the length of this one, which is a quarter wave length, okay? And so you substitute beta L, you substitute for the L lambda over 4, and beta is 2 pi over lambda, and this quantity here becomes pi over 2. And from the tangent hyperbolic function um, um, evaluation, you can see that this really, what happened, this will basically tend to go to infinity. So the way to solve this in this case is we take the limit as this quantity goes to infinity. So you end up with dividing this by infinity, this by infinity, and you end up only with this piece here, z lambda over 4 over z load times z lambda over 4. And that's what you're getting here. Okay? And of course, this is the input impedance, but we're not interested in Zn because we want Zn to equal to Z out in this case, okay? So what we're trying to do then is solve what is the impedance that is required for a quarter wavelength impedance matching line to satisfy to have a good match. Okay, and that's basically from this equation. You can actually what you need is to solve for this. Okay, and you solve for this. This multiplies by this, and you take the square root. And this is the famous equation of the impedance required for the quarter wavelength suction for matching, which is basically the square root of the geometric mean of Z load and Z zero. Okay, and that is in this case here. Zn is really ZO in this case. Okay. Now, this is a single section, of course. Now, a single section, you end up with just a single pole, basically a single resonance, okay? And this tends to be narrow. This may not um, be acceptable to you. The return loss would be not acceptable throughout the whole bandwidth, and that's when you when you add more sections, and by adding more sections, you actually get a broad response. And that's schematically, that's how we draw it. We draw the load in here, the source in here, and in between, we have steps of impedances to get from this value to this value. Okay? And that's what we're interested most of the time. So now this can be implemented in waveguide as well. So if you have two waveguides, one waveguide in here with a different height than this waveguide, and I'll show you in a minute, you might recall that the impedance of looking into a waveguide is basically proportional to the height. But they have to be the same width, though, the same width, so that the propagation mode is the same, the cutoff frequency is the same. Now, in this case, you can actually add another piece of um, quarter wave waveguide, and then the height of that waveguide, intermediate waveguide, the matching transformer, would actually follow this equation in here, so that if the impedance of that waveguide would be this, and from this you can figure out what the height of the middle of the matching transformers like. And just to skip ahead, this is basically what it is. So you end up with one waveguide here, one waveguide here. In the middle, you put a transformer, and that transformer basically matches this, just like you would do in the case of a microstrip line. Okay? So now, how do we design these things? Of course, if it's a single order, then it's a simple equation like this. Okay? And this you would interpret that into waveguide height, okay? But what we do basically is, if you can use MATLAB, okay? MATLAB has an RF microwave design toolbox that you can get, and in there you can go in and specify input impedance, output impedance, and then how many sections you need, or it would solve for you how many sections you would need, and then you specify what type of transformer response that you would want. And these types, you can refer back to Bozar book. We got Chebyshev, we got polynomials with Chebyshev, and other ones as well. But I picked just basically the Chebyshev, and basically the tables, the design tables are like this. So the first thing you would need to do to figure out is the load over input impedance, or the source impedance ratio. So this impedance over this, and the tables are listed right here from 1 to 10 for 2 sections, 3 sections, and 4 sections. Okay, and of course the gamma, which is the gamma m, that's basically the maximum reflection that you would tolerate, and that's for instance in here 0.05. And as you recall, now that gamma, and in terms of return loss, you just take minus 20 log of that value. Like in this case, the 0.05, that is 23 dB of return loss. Okay, so like in this case, as an example, And this example in here is, let's assume that we're trying to match 100 ohm to a 50 ohm line. Okay, this is not waveguide right now, of course. This is just as a generic example, just to illustrate the idea. So we got Z load 50, 100, and characteristic impedance of the input is 50 ohm. And so we take the ratio in this, and you basically get 2. Okay, so you come down here and you go to 2, and let's assume that I want it in to be 3. Okay, based on this value here, 0.05, or no, 0.05 here, and n is 3 in this case. So you go from the ratio is 2, you go over to the corresponding entry of the table, and you get Z1 normalized by Z0, Z2, Z3. These are the three transforming impedance transforming transformers. Okay, these are the sections. So the first section here, second section, and third section, and you got 1.14, 1.4, and 1.7. Okay, so basically denormalize these, and you end up with these values in here, and that's what we have schematically in here. Of course, now with these, if you're implementing these in coaxial waveguide or coaxial line, you would go and pick the radiuses and the outer shield with the diameters that would fulfill this value. If you're doing a microstrip implementation of this, you would basically take these impedances and put them into the Wheeler's equation and come up with microstrip. Depending on the substrate you're using, you would get different widths. Okay, so, and that's what you would get. Okay, so this is pretty simple. So we're going to do the same thing, except we're going to do it for a waveguide. And in a waveguide, we got a little different um, way of doing it, because in microstrip lines, we're dealing with widths that correspond to impedances, but in waveguide, we're dealing with heights that corresponds to impedances. Okay, so now this is the table, but if you're just doing, which is the most common situation you get into, is either you're using a two-section or a three-section transformer. And those, Bozar and many other people derived the equations for those. So you could very much just basically compute these, and then you would not have to worry about all these tables. Okay, so we just basically, for instance, if you're trying to match Z1 to Z2 in this case with two sections that are ZA and ZB, these are the equations. So it just basically the ratios of Z2 to Z1 with various power square roots to the n power somehow, or 1 over n. And the same way correspondingly for the three sections. And that's what I'm going to do today. I'm basically going to build a few of these waveguide transforming. Like in this case, this is a single section. So I have a single waveguide in here. This is a matching waveguide for this input waveguide to this output waveguide. Okay. And I also have a higher order one, this one in here, which is from the, I'm going to show you in a minute. This is from the Matthew book, okay, which is even before I was born. This was used as an example in his book that was in the 60s, written in the 60s. So we got an input and an output, and I'm going to use three sections to match this, okay? And we're going to go through that in a minute. Okay, so we've got these equations in here. We can do that, or we can just go to the tables. And these tables, if you type on Google, just basically Chebyshev or binomial polynomial impedance matching tables, you can find these in hundreds of places where you can load them for various lengths and values and so on. Okay? All right, so now let's do a multi-section matching transformer, introduce that concept. So basically, So what we're trying to do, we've got a waveguide in here that has an A1 to B1 um, dimensions. And we've got another one that is A2 to B2. And what we're trying to do now, we want to attach, if you attach this to this, you get a mismatch and you get bad VSWR. So what we're trying to do is minimize the reflections. So that's what we have to do is insert A by B waveguide, which basically transitions the impedance so that you get minimum return, maximum return loss negative, of course. And that's what we are trying to do. And the length of this is a quarter wavelength, of course. And that is quarter wavelength, not free space, but in the waveguide domain. Okay, just like you would do if it was microstrip. Okay, which is lambda g. All right, so let's do as an example, illustrate this. So let's try. So how do we do that? Well, we do that first of all, the Z load in here and Zn in here, this waveguide in here, impedances. We figure out that the impedance of this waveguide in here has to follow this equation in here. And this is what I derived back here. Okay, that's just simply this. And so from that now, we can from this value, we can figure out what B has to be. A, of course, this section in here, A is the same value as A1 and A2. These are all equal. Okay. So what I'm going to, and then in that case, knowing this is the free space impedance, 377. Epsilon R is air in this case. I don't have any medium inside. Okay. So we've got A is known, and then we solve for B, and that's all it is. Very simple. Okay. So let's take an example. This example here is two waveguides, and the length of this one, the input, the output, and the length of the input is arbitrary. You can have any length that you want, but the matching suction has to be a quarter wavelength. So we've got in this case, for instance, is in this case the input in here. Let's say that it was a 6.5 inches. That's the width, and this is for L band. That's why these dimensions are huge. And then the height is 1.3. Okay, and then the output. Let's say the output in here was the height in here was 3.25 inches, and then I mean the width and the height is actually the same as A1 in here, which is 6.5 inches. Okay, so how do we match this? And this basically you would exactly perform this, and you come up with this section in here. So in the equation, if you use this equation in here for the input and output, you end up with 150 for this section and 376 for this section. And in that case, the transformer will have to be this value here, according to this. Okay? And then from that, you solve basically for the B, and it turns out the B transformer has to be this value in here. Of course, I converted this to millimeters. Okay, so let's look at this. And this is the first example, which is this. And that's what I have in here. So I have this section in here. Okay, so as you can see, this is the waveguide, how it's hollow from the inside. And we've got a staircase showing you the step between the output to the input. And this one in here is the lambda over 4. That's basically the transformer section, which is this. Okay. So I constructed this, and when we basically put in the excitations on this side in here, I put in TE10 excitation, and then pick up the same signal on this side. And the response basically was this, as you can see in here. Okay, so basically you got a single resonance, and you can see that the bandwidth is relatively narrow because you got a single suction. Okay, and this drawing in here, you might say, well, why is it looking funny? But no, this is fine. I just wanted to span wide so I can show the cutoff frequency because I know what that value is. okay, and then so on. Now the computation of this, oops, okay, I don't want this. The computation of this, of course, I carried it in MATLAB, so I'm gonna make sure I give you enough time if you're watching this to freeze it so you can copy this, try this. So basically we define the dimensions in here, the mode, the free space impedance, okay, and then basically compute the various ways of doing this, and this is the result, okay, where you end up with this one giving you the transformer. So now, if you can come into this, if you don't like this, you can just zoom in basically, and you will see your typical nice um, performance characteristics. So this is the return loss, and this is the insertion loss. Okay. All right. Okay. So let's look at the uh, the E field on this. So basically, we got the E field is this here. So now what happens is the E field is basically the signal is injected on this side and it comes out on this side. Okay. Excuse me, let me just pick up the phone. Okay, so let's look at okay. Let me just turn this down so we can all right, so basically, why do I plot this? Because a lot of times, if you look at the bottom of this, you can see that if somebody doesn't tell you this is really a stepped transformer, you can see that it's just single waveguide, even though we have three different heights. Okay, you can see how these are. The other thing also is you can see that the middle section in here really, if it was really coincident with the quarter wavelength, it would have to be exactly at a half of one of these, in which in this case it is not. And the reason it's not is because you can see it in the frequency response is because I really intended this for 1.3 and it is not at 1.3. It's more like I would say this here, M6, which is 1.24. So really, this because of the step parasitics, the this section in here theoretically equal wavelength, but really you need to tune it. So, and I did not tune it. So, and you can see that really clearly by viewing, let's say this. This is if it was really a quarter wavelength, this would have to be sitting right in the middle of one of these because as you can see from the pattern, okay, each one of these repeating patterns from here to here is a half wavelength. And from here, from the null to the middle of this is a quarter wavelength. And that is, you remember that from the fundamentals of propagation in waveguides, okay? So basically we have this, and so let's animate this just so that we can have more fun viewing this. You see, here is the waves are coming in here, and there they basically you can see how they transparently step through the step and just transform into a TE10 in a different height waveguide. Okay, and yet if you look in the back, it's really transparent. It's exactly a waveguide. Okay. All right. So let's close this and let's go to another example. Okay. So we're going to go to okay. So we've seen this. We're going to go to this example here. And this example, I took it from the Matthew book. This is a book here, the Microwave Filters Impedance Matching Network. and coupling structures for most applicable applications. So we're gonna do this example in here. So this example, Matthew did this where he's trying to match a waveguide, which is the input is 1.3 inches height, and the output is 3.25 inches. Okay. And then the width of the guide is basically 6.5 inches. Okay. So let's go through that example. So okay, so let's first start with basically the way this example was solved. Really, um, we need to have a three section transformer that transforms the impedance of a waveguide that has a height of 3.25 to another waveguide which has 1.3, okay, inches, and this is for L band. The of course, the width of the waveguide, the broad width of the waveguide is 6.5 inches. Okay, and like I said, this example was detailed, and you can go back to this book. This book is available on the internet. You can just type Mathy and this title here, and you'll get it. So if you go back to these tables in here, I solved this, and it turns out you would need three sections that have these impedances in here, okay? And the way I did this in MATLAB, this is the code, okay? So basically, I put in this, and then I solved the equations based on basically this equation in here, the three section. This one in here, this is three section. These are the three impedances. So I calculate Z1, Z2, and Z3. And these are the three stages, three sections of the waveguide matching transformer. And that's what I get in that solution. That's what I get in here, the calculated. These are the implementations you can see. And then I took the tables also. I did pick up the values from the Beaux-Arts tables, which are these tables for a three section. Of course, that would be n equal 3 here and 0.05 in here. And then the ratio of the impedances that corresponds to whatever that impedance value was. And this is basically this is the code to solve these. Both I want to compare the values from the table, these values, to these ones from the computed closed form analytical solutions to this, and that's what I get. Okay, so basically the Zn, the first Zn is 150. Okay, and then the load is 376, and the ratio is 2.5. So if you go back to 2.5 in the Beaux-Arts table in here, 2.5 sits in the middle of this. So you would have, and of course, N is 3 and gamma is 0.025. So that would make it sit right here between these two rows in here. And what I do is I use interpolation between these two to get to the actual values. And that's what I got basically. When I do that, I get these values in here after you take out their normalization. Okay? So, and then the closed form solution is these ones in here. So when you look at these compared to these, they almost come exactly the same because they're really the same ones, except these came from a closed closed form solution, and these came from the tables. And the corresponding heights of the three sections, these three sections, this section, this section, this section, are basically here. And when you look at these heights to these heights, they're very similar, if they're not exactly the same. Okay? So this is the way this was done. So I've got an input in here, an output in here, okay, and an input in here, and I've got three-stage transformer that transforms the impedance basically between this waveguide and that waveguide. Okay, and that's what I get. These suctions in here. These are the heights. Okay, and let's go to this here. So we're gonna go to the second example. Let me close this first. Minimize this. So we're gonna go to this one in here. Oops, no, not this one. Okay, so I've got this one in here. So this is the so I've got the input. So we've got an input. This is the input section. This is the output section. I've got a three-stage transformer. Okay, a waveguide transformer, and this is basically all it is. It's a hollow waveguide, and you can see that, okay, with a 1 millimeter thick metal in there, and that's how I created this. And I put in the input excitations to this, and so we've got the input and the 1 and 1, 2 in here. It's reciprocal, so you put either way it would work. And if I run this, basically this is what I got, the response. And you can see the response is nice and very broad. You can see really nicely. And of course, this one is much wider than the first example that I did, which was this example in here. As you can see, this one in here. Okay. So, all right. And so this is the return loss in here. This is the insertion loss, and get nice one. And of course, this is where the second higher order mode starts to kick in. Okay. All right. So let's look at the E field as well. And this, so this is the E field of that. And you can see that it's pretty nice. You can see how what I did is I didn't extend the length of the input and output very long. So you can see that how nicely this is. It's from this side, it would look as if it's just the same exact waveguide with the same heights everywhere. But when you flip it over, really what we have is a multi-case, multi-steps, 1, 2, 3, 4, four-step transformer. Okay, and so let's close this and go further. Now, so the next next example I want to really look at, I grabbed this while looking back at a patent by somebody, and this was interesting. The patent is not on the transformer; it was on something else. But I said, let me try this. Um, so I have on this side in here, I have a square waveguide. Okay, and in this case, in this side, I've got a rectangular waveguide. And the reason I was looking at this is because I have a series on KA LMB feed structure designs that I just finished. It was an 8-part series, and you can go back and refer to this. It's these ones in here, okay? And in that one, we dealt with a horn that was interfaced, a circular horn or a square horn, a square waveguide or circle waveguide. And so what I wanted to do is basically look at a square waveguide on one side. This is a square waveguide in here, and the blue cover on the inside is basically the air. Okay, and I wanted to use a two-section matching transformer to transform it into another waveguide, a standard waveguide. This is a standard, I think WR34 in this case. So I wanted to do matching, and I want to do this based on the closed form solution that is basically, let me go back and show you down this one in here. So I'm going to use these two equations to come up with two sections that will interface, or come back here for N2 0.05 and figure out the impedances for such a transformer. Okay. And so what I did is I took this here, and these are the widths. The rectangular waveguide was WR34, which is zero point 0.3 by 0.17 inches. Okay, and and then I took a square waveguide, which was 0.34, same as the width of this input one. Okay, the height and the width is the same in here. And the reason we do this is because remember on these dishes, on these antennas, if you have an antenna structure in here, you're trying to match the aperture of a waveguide to a horn to match the 377, which is the free space characteristic impedance. And if you do that with a rectangular horn, a rectangular waveguide flared horn, uh, the impedance is not as good as the square waveguide. Okay, the square waveguide, because the impedance, if you look at the impedance on here on this equation, go back to this here. Now, this is for rectangular waveguide. V over A, if it was a square, this would go disappear completely. So you've got this impedance in here, which is closer to the characteristic impedance of the free space. Okay, so you end up with a better return loss. And that's what I got basically. So I wrote this MATLAB code in here and did the same thing, except I solved for the transformer one, transformer two, the heights. And that's what I got basically. Okay, these two sections in here. Of course, the length of these is a quarter wavelength. This is for, I did this at a center of 25 gigahertz. Okay, and this is what we end up. So let me go back to this one in here. So I ran this. Okay, and if you look at this, the excitation is in the this one in here. Of course, the square waveguide. Of course, you've got two modes. It's just like a rectangular, just like a circular waveguide. Okay, and then on the other side, I've got a single mode pickup. Okay. And when I run this with these dimensions, I got okay. This is basically what I got. So the return loss is here, pretty nice, and it resonated just as about I would say 22 and a half, not 25 gigahertz. Um, no, this was not done for 25 gigahertz. I apologize. 25 gigahertz would be past the first area where it overlaps with another mode that propagates in. Okay, so I got this resonating in here, and it's pretty nice. And so with two sections, I get a good thing in here. So if you were to, let me see here, if you were to look at this, say from a 15 dB, this is 20 dB in here. So if I were to go to the middle of this would be this. And of course, I would go to here. You can see from M5 to M6, M5 is 19.4 to 25. So 20 to 25 gigahertz, you can see that this is usable. And of course, if you look at the E field of this, this is what we've got. So basically, the dimensions are longer than a half wavelength for these two pieces, and that's why you see it repeating. But the middle ones, you can see that it's a half of the pattern of the E field corresponding to a quarter wavelength, okay? All right, so having done this now, so what do we do with this? Well, what we do with this is I'm gonna go further and look at two situations that I've already covered in the past, which we want to detail them in this case, which are these transitions for an LMB. I want to go from microstrip to a waveguide dimension in here, and I'm going to use a multi-section transformer, a waveguide transformer, to match from this to this. Okay, so basically I'm going to go from 50 ohm to this particular waveguide in this case. And I have another example, which is this one in here, okay, which is a substrate integrated waveguide. I want to go from here to the same waveguide, and I'm going to do a little comparison between those two. And today I'm just going to introduce the performance, but I already did this on one of my videos, so you can refer back to those, but we're going to cover it next time. So this one, the first one, that's this case in here, the macrostrip to waveguide transition with waveguide transformer impedance. That's basically 1, 2. This is a 2-section transforming. And the other one, let's see what I did for the other one. The other one, we've got also 2. Okay, so on this one in here, the response of this was from M1 to M2, basically from 21 to 28 gigahertz. Okay, so we're going to go through this one, and then let's go through the other one, which is this one in here. Okay, the other one, we're going to go from M7, which is 20, to M9, which is 28. Okay, and that's basically so these two examples in here. So, oh, okay. So basically, this is what we're going to do for the next videos. Is we call this an inline. Um, this is called this class of transitions. They're really called inline transitions between a waveguide and a printed line. Okay, so we're gonna basically do this where we take the waveguide transformer, impedance matching transformer that we just covered, the principles of that, and we're gonna basically, this is taken from some of the IEEE publications. We're gonna use this transformer to feed an antenna assembly to an active circuit section in here using a microstrip line. So what we do is we go from a microstrip line, and then we flare out in a tapered line to match to a small insertion of dielectric material into the waveguide. That would be a dielectric filled waveguide section. And then we go from there to the full height waveguide, but using via a transformer, an impedance matching transformer implemented in waveguide. Okay, and this is basically, this is how we construct this. Okay, so we're going to cover this in the next videos. I already did cover one of this. In if you go back to my channel, you can see it. Here's one video, and here's another video, and here's another video. These were covered in here, but I didn't cover them thoroughly. So what I'm going to do in this case is we're going to get a closer look at some of the publications, like in these cases, this one here from IEEE. And here's another one where we have this is, they call this substrate integrated waveguide, except without vias. You know, they use these um, quarter wavelength open line sections on the sides to implement the shorting via. Okay. And then what we're going to do is we're going to design this. So basically, we're going to have to design first this section in here, this section here, and then design the next section. And that's this one here, if you look at the side view of this. Okay, and how we design this is basically really straightforward. First of all, we design a taper or stepped. This could be tapered or stepped quasi-TEM microstrip line transition to 50 ohm between the dielectric filled waveguide and the microstrip line. So this tapered line matches the first transformer section, which is basically that introduces the dielectric material into the waveguide, which is just a dielectric filled waveguide that has the same height as the substrate. Okay, which matches that to a regular microstrip line. And then we go design a waveguide multi-section Chebyshev transformer. Well, it doesn't have to be Chebyshev. Could be any other family as well, but in my case, I chose that. impedance to match a electric field waveguide to a standard waveguide. And that's what we just did today. Okay. So we're going to use the principles that we developed today to do this here. Okay. So another view of this, of course, the length of this transformer in here, this is really a transformer also between the electric field waveguide and the 50 ohm microstrip line. This is we use a 3/4 of a wavelength to do this here. Okay, while these ones in here are really a quarter wavelength, the inside the waveguide. Okay, so basically we're gonna do these two. We're gonna redesign these, except this time we're gonna use more details than the first video. So, okay. So this is it, ladies and gentlemen. This is Dr. Mohamed Nezami coming to you from Garage, Jordan. I thank you for for viewing this. Please, if you don't mind, I would appreciate if you could go to the my channel here and please sign up for the channel and subscribe and share some of these videos so that I get more views on this. I would appreciate it. Okay. And again, Dr. Mohamed Nizami, thank you very much for watching. I'm coming to you from back here, as you can see in the picture, Jerash Jordan. We'll see you in the next videos, two set of videos that are going to be hopefully very interesting and very beneficial to you. Thank you, ladies and gentlemen, and have a great day.